So pause on where you are there, and forgive me, it's a little small, but I think you guys can see it decently. So when 50 grams of potassium chloride is dissolved in 100 grams of water at 50 degrees Celsius, the solution correctly can be described as what? So all you have to do is what? Find KCl, which is this kind of blue line here, and then look at what? 50 degrees mark, so down here, and then what? Go up from the 50 all the way up to till you touch the line. So that dot right there is representing what? A saturated solution. So at 50 degrees, how much should dissolve? 42. Exactly 42 grams should dissolve. If you have more than what the saturation point is, then you're in a supersaturated solution. If you have less than that, then it's unsaturated. So that should be what? That should be a supersaturated solution. Yay! We're at 100% so far, guys. All right, so let's look at this one. When 20 grams of potassium chloride is dissolved in 100 grams of water at 80 degrees Celsius, the solution correctly can be described as, we're looking at who? What solution? What line? Kind of browny red one here, potassium chlorate, but looking at what temperature? 80 degrees over here, and then you bounce all the way up to the line, and how much should dissolve? 38, 39, someplace up there, not quite 40. So if we put 20 in there, what could happen? It's not saturated, so it's unsaturated, so I could add upwards of how much more? Say again? 18, 19 grams more, and it would all dissolve. But once I surpass that, then it's super saturated, and it would probably just kind of crystallize out, and it would be that grimy, sugary stuff on the bottom of your sweet tea if it wasn't all the way dissolved. So give me a thumbs up if you can determine something super saturated, saturated, or unsaturated based on data given like this. All right, let me do one more. So it helps if you participate in the survey, because then I know how much time to spend here. All right, so let's look at this one together. Solution potassium chloride is 20 grams of salt dissolved in 100 grams of water at 70 degrees Celsius. How many more grams of salt can be added to the solution before reaching the saturation point? So again, we're looking at what temperature? 70 degrees Celsius. So then we go all the way up to the potassium chlorate line, which is right here. How much dissolves at 70 degrees? Approximately 29 or 30, right? Kind of depends on how close you get there. So if 30 grams dissolves at 70 degrees Celsius, and currently it has 20 grams of salt dissolved, how much more do I have to go? 10 more to go. So basically that means I'm down here at the 20 mark. I'm right there, and I can add up to 20 to 30, so that's a gap of 10 grams of potassium chlorate. All right, looking forward on yours, which one can I go over? Yeah.
Can you do like a create and destroy solution?
Okay, that's the only one I knew that you guys would not know how to do. This one?
Yeah.
Okay. So cerium, this is because we're talking about solution enthalpy of solution shortly, maybe today, maybe tomorrow. So when cerium sulfate is dissolved in water, what you can see is that cerium is the only salt, and I can say salt because salts just mean what? And anything ionically bound, right? Salt's not sodium chloride, it's anything ionically bound. You can see it's really the only one that drops in solubility. So what happens is at higher temperatures, it's what soluble? Less or more? Less. Okay. So at higher temperatures, it's less soluble, which is odd. Most of the time, all of our salts, generally 95% of them or so, increase in soluble at higher temperatures. So when blah, blah, blah is dissolved in water, energy is likely released because it wants to become more stable, and stabilization means that you're at lower energy, either entropy or enthalpy. So overall, as it dissolves, it's releasing energy, because what you can see is that as you go in higher temperatures, where it should be absorbing, it's not dissolving. So you kind of had to look at the trend and then think about which of those would create the best, the likelihood of it being dissolved. So don't worry about them right now too much. Okay, so let's stop on solubility for now. So we're going to do a couple calculations, so have your calculator out. Some of them are going to be very similar to things we've done in the past. It's just looking at units and then thinking about how to achieve that. So either halfway close your computer or all the way close your computer. Make sure you get some space on your desk there. My goal is to do at least, you guys with me? My goal is to do at least 2 questions per type of question, and please make sure you're listening closely, writing down examples. I have to bring my grandfather to the hospital tomorrow morning for a surgery, so I will not be here. So what I'm doing today is hitting you hard with notes so that tomorrow you can practice. But if you practice enough today, tomorrow should be a piece of cake. Okay. So the first idea is just making sure you know what solvent, and solution are. You can draw yourself a quick little diagram, cartoon even. You can make it cool, or you can make it like the boring images in your textbook. But whatever works for you works for me. So take 1 or 2 minutes and draw out a picture. Oh, what you I'm literally giving you 1 minute right now, and I want to make sure you're trying to draw the solvent solution interaction, because that's probably one of the not really tricky things. It's just making sure that you understand what each of those terms mean. So you can even draw it similarly to how we did some of our particle diagrams when we were doing lab. So at this point, we should be drawing it. So when you're drawing, and maybe you can think of it as like Kool-Aid. I'll just give an example first. Kool-Aid. Well, Kool-Aid's not just Kool-Aid, right? What's inside of it? Okay, powder. What else? Kool-Aid. So I heard powder. What else? Sugar and water. What else? What makes it colorful? Say again? Okay, red 5. I think I'll go. We'll go blue 3 or whatever it is. All right. So we got blue Kool-Aid up here. It's purpley blue. So which of these is the solution? Everything. Okay. Trick question, right? So the whole thing is the solution. The entire thing is the solution. What is the solvent? Water. And why is that considered the solvent? It's what? Well, isn't everything attaching to everything? Right. Well, I could add the water to the Kool-Aid, right? So it's not necessarily about an order of operations. It's not necessarily about things interacting, like everything interacts, right? The best guess I can give you is that the largest quantity is going to usually be called the solvent. The solvent is usually in larger quantities. Generally, like I have a lot of water and a little bit of solute. So you can kind of think of it in the quantity standpoint. Or most of the time, if we have a solution, sometimes it's a solid liquid solution, right? So we had a solid and we added a liquid and we got our solution. Well, many times if we're doing that scenario, the liquid is considered the liquid solvent and the solid is considered the solid solute. So in this case, what's my solute? The powder, whatever the powder is, the sugar, the little blue food coloring dye. We have a lot of different solutes, so they don't all have to be the same thing. And you can actually kind of imagine, if we're dissolving them in water, they're interacting with water. What are you trying to say to me? They interact. What's a more advanced term for interact? Or what makes them interact? Some sort of polarity with the compounds, so the properties of the compound. And so in this case, the water being polar, you know water is polar, as you draw it, you've drawn it a million times. So it's polar, it's got a partial negative end and a partial positive end. It must be interacting really well with the sucrose here and the blue food coloring, which is actually polar. and whatever this powder substance is. It's interacting really well, because if it didn't, it would make a layer of water and then like blue powder sugar stuff. It wouldn't be a solution. So what's the term that means it doesn't mix? Okay, insoluble. What if I told you, say again? Immiscible, right. So there's actually another term, immiscible. Miscible means it mixes, and immiscible means it doesn't mix. So we're going to get to some of that terminology today and then do some calculations. So I, of course, have a cartoon for you. I just love hanging out with you, chlorine. Sodium. Oh, no. Is that water? What? Where? Dun, dun. Dun, dun. Dun, 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 dun. I'll never forget you, Mom. I know it's a sad morning. But it's traumatizing when poor sodium chloride, in this case, sodium chloride, is ionic, and when it interacts with water, it actually forms a special intermolecular force, not lone dispersion, not dipole-dipole, not hydrogen bonding. It actually forms ion dipole, which is just an extreme of dipole-dipole. It's more about the fact that there's ions and water with the dipole moment interacting. So it's really strong. So most of the time our solutions with ionic compounds are super, super traumatizing. All right, so let's go ahead and move on to our miscibility, just referencing a couple terms that might be on your reading guide. So if you want to check them off in your reading guide, like, hey, we covered these, let's make sure we study those. It would be interesting to do that from your notes or from your reading guide, whichever works for you. So we talked briefly about how these things interact. Just make sure that you remember they don't interact because they want to, they interact because they have to, due to the intermolecular forces that are naturally present between these types of molecules. So in this example here, what am I kind of just told you this, but what would be causing water to interact with sodium? What IMF? Say again? This is ionic, right? These two together ionic. Ion dipole. So it's actually a fourth intermolecular force. We don't talk about it unless we're in solution, because think about it. When do we have water? We don't talk about ion dipole moments or ion dipole interactions unless we're in solution. And that makes sense because we don't have water interacting with things all the time. It's usually once it's in an aqueous solution. All right, so here's another example, and these are kind of just good particulate diagrams to let you see what's happening up close. So we have this, this is hexane, C6H12. Okay, that's hexane up here in the black color up here. And then we have water down here. Well, if I'm looking at this guy, hexane looks like this. And I can draw 1, 2, 3, 4, 5, 6, and there's carbons in a straight line, and then there's hydrogens all the way around it. If you're looking at that long carbon chain, do you see that as polar or nonpolar? Say again? So looking at the car, and there's hydrogens all the way around on these little dashed lines here. Do you see an equal distribution or an unequal distribution? Equal distribution. Is that polar or nonpolar? That is nonpolar. All right, so the fact is that hexane is nonpolar. It will not mingle with water very well because of its differences in polarity. Yes? Yeah, that's a 14. I'm thinking pentane in my head. Thank you. So 12, 14, yeah. So in the case of the polarity aspect, though, this intermolecular force is going to experience, or this molecule is going to experience London dispersion, which is basically based on the fact that you have a large electron cloud surrounding the carbons, and it can just distribute a little differently on one side versus the other, and it creates a little bit of a polarity. So they interact really well with each other, but that won't really interact well with water, because water has a strong polar moment, and it can interact via dipole-dipole and hydrogen bonding. So do you see them blending well here? Yay or nay? No. There's one water molecule here, there's one hexane there, but not well. So would you call this more of a homogeneous or a heterogeneous mixture? Hetero. And would you call this miscible or immiscible? Immiscible. So just try to make sure we can speak the language, especially if you're reading something, you're comfortable with that language. I have another picture. Oh, no, never mind. Good. All right, so keeping that in mind, we already know one factor that will affect whether something will be soluble or insoluble is what? Polarity, right? Just the nature of the molecules. What else? You guys do this every day. If you're mixing something with something else, how can you increase its solubility? Stir it. That's called agitating. You guys are good at that? demonstrating. What else? Okay, so increasing the temperature. What else? Do you guys get those grinding the powder up? What does that mean in chemistry sense? So either more surface area, right? It's actually more surface area. So you guys hit it on the dot here. You guys seemingly know what you need to do to increase the solubility or the rate of solubility, increasing the rate of something dissolves. So the nature of the solute and solvent here, that many times it's just going to deal with the properties of polarity. And so if they mingle well, they should start to dissolve really well. Increasing the rate at which you're stirring something, which is agitation, that's another factor. It'll just increase the rate, means it will dissolve faster. Faster. But it will not change the amount. Like, can I indefinitely stir sugar into coffee? No, it's going to stop dissolving eventually, and it's going to kind of get crunchy and kind of build up on the bottom of the coffee mug or whatever. So it's not going to dissolve indefinitely. Stirring just changes how fast it dissolves. Same thing with temperature. Temperature increases the rate at which it dissolves, so it makes it dissolve faster. That is if you increase the temperature. If you decrease the temperature, you can probably imagine it slows down the process of dissolving. But eventually it will max out at a particular amount and it can't dissolve more. And then the surface area. Powdered sugar versus a block of sugar, which one will dissolve faster? Powdered sugar, because it has what? This one has more surface area. This one over here has less surface area. And surface area is just the culminating or the accumulation of every face of that sugar crystal. So a big, huge block of sugar might be pretty big, but compared to all the tiny dots that I can draw from a powdered perspective, their surface area actually is way, way, way bigger than the block of sugar. So it'll increase the rate, generally not the amount at the end, because we could let the block of sugar dissolve for hours and it would dissolve, but it would definitely not be, the coffee wouldn't be hot anymore, right? So we would kind of be in a place where it was inconvenient to do that. All right, so some of this was in your reading guide. So I'm just hitting the highlights here to make sure that you're reminding yourself of some of the things that you read earlier. Okay, so the term like dissolves like, you read that. You've seen my awesome polar bear video. How many times now? Two, okay, maybe three. And so with that in mind, I show you the polar and polar interactions, and then I show you the non-polar through the grizzly bear, the brown bear examples, because it gives you an idea that that's kind of the trend. But many times we shouldn't always just say like dissolves like, because it doesn't really tell you, or it doesn't tell me that you know what you're talking about, because you're just repeating a phrase we've said 13 times, right? So the idea behind like dissolves like is that they intermingle or they interact well together because of their similar IMFs, which means they have similar polarities. So that's the meaning behind it, or the reasoning behind that phrase, like dissolves like. We just know that they interact well because they are like magnets to each other. A partial positive and a partial negative attract. A partial positive and partial negative attract. They might attract through dipole-dipole, ion dipole, or hydrogen bonding. So anything that's polar will interact through dipole-dipole, hydrogen bonding, or ion dipole. But that still means that they're similar in their polarities. What about a more of a situation where, let me do this other one, nonpolars interact? Yes, they're going to interact through London dispersion forces, and lesser so on any of the other accounts. And this is what we drew in our beginning of the enthalpy lab. We might finish. We might. Hold on to those papers. So the terms that you've been saying, and this is more the making sure you know how to spell it if you need to, the terms you've been saying that reference the ability to mix or inability to mix would be miscible and immiscible. So immiscible would be like this fantastic lava lamp as the oil mixing with the water. It's got a little oil on it. Looks like moisturizer. Is the oil interacting with the water? No. Okay, so it's not. So it's going to be called immiscible. And that's because many times methane, oils, greases, gasoline, and fats, other lipids, yeah, those are generally nonpolar, so they don't interact very well with polar water. Okay. Take another second there. Some of this is repeated from your reading guide. That's why I'm hitting the highlights, making sure you guys are taking notes smartly, writing down what you need to, starting things in your reading guide, whatever it may be. So the last phrase down here, or last bullet, oil or grease will dissolve in acetone or gasoline. Well, we know oil and grease are what kind of molecules? Say again? Nonpolar. So what can you conclude acetone and gasoline are? They're probably nonpolar to an extent. Acetone is nonpolar on one end. It's kind of a larger molecule. Gasoline certainly is nonpolar, but acetone has a slightly polar group, but it does interact well with some nonpolar substances. So the last picture down here just gives you another idea of what you're looking at from the perspective of the particulate diagrams. Oh, no, sorry, it's on the next slide. These are actually just examples. So do you notice something similar with most of these nonpolar solvents? They're all what? Carbon and, right, so they're all organic compounds, generally carbon and hydrogen. Not really much else. There's one chlorine and an oxygen down here, but they're still fairly nonpolar. What do you notice about the polar solvents? They have carbon, hydrogens, and a couple of oxygens. There's a nitrogen in there. It's likely because these oxygens here have lone pairs. The lone pairs give that partial negative aspect to that side of the molecule, which creates the polarity that we've been speaking of. So there is some similarities in their formulas that might give you a little heads up on what you're looking at. Okay, read this first, and I'll talk. Read this first, and write down what you need to really talk. For this first bullet up here, what kind of diagram have we been looking at that's been showing us that same thing? Solubility curves, right? So the solubility curve looks like grams of solute over grams of water, and what on the bottom? Temperature in degrees Celsius. And we see those little lines are going to go up like this, and it's basically just showing us generally the temperature, as the temperature increases, the solubility of a solid, like an ionic compound, will increase. But we did see one or two that had the opposite effect. We saw this little decline. It was like a dashed line. Maybe there were two of them, but they're supposed to be indicating to us a different type of substance, which is a gas. And that's really common knowledge. Like, you know that if you want carbonated beverages to stay carbonated, where do you put them? Oh, in the freezer? That's when you get a slushie. Where else could you put them? Just in the fridge. You wouldn't put them out on the deck, right? Let's heat up the soda. It's going to be really carbonated when I get out there. No, we always make sure that we put it in the sun, like kind of a colder atmosphere or colder temperature, because we want it to stay dissolved. So where is that represented here? On the left of the graph or the right of the graph? The left, right? Colder temperatures over here means that more gas is dissolved and we get a nice bubbly carbonated beverage. Whereas over here in the warm outdoor temperatures, that baby is flat and the soda is disgusting, right? Because it's just like sugar water. So the reasoning why, though, is because of the increased kinetic energy that these gases feel, and so when they start to get high in their kinetic energy, which is energy of motion, they pop out of the top of the surface of the liquid, leaving them less dissolved. There's lesser gases in that given quantity. So if you wanted to increase the solubility of your gas, and you couldn't really monitor or maintain the temperature, what you could do was wait to open your soda. Before you open the soda, what's in the top of the soda bottle? Gas. And what does gas cause? What does lots of gas bouncing around and colliding with the container walls cause? Pressure. Right, so we have my little here's a soda bottle. Looks like a soda bottle. Okay, so we have our soda with our carbon dioxide bubbles in here. So what's up here? What kind of gas do you think? CO2. They pressurize the top of soda bottles by pumping in extra CO2 to keep it really, really carbonated. But it's actually because it increases the pressure inside of the container. So when you open the container, what do you hear? What's it doing? Releasing the gas and releasing the pressure. So then you start to get all the bubbles that kind of bubble up, and you're like, oh, close it before it overflows. So that's actually just pressure being released and gases going out to kind of meet equilibrium with the atmosphere around them. So this increased pressure does cause an increased solubility of the gas as well as in a closed container. It stays really, really concentrated. It holds the bubbles kind of in the surface of the water or the solution or whatnot. So there's a relationship. Increased pressure will increase the concentration of a gas. So then you tell me, what's the alternative to that? Decreased pressure decreases the concentration, right? So there's a direct relationship. As one changes one way, the other one changes in the same direction. That's the directional proportionality of pressure and solubility of a gas. It's not true for anything else, it's just a gas. And we do have this guy, his name's Henry. Yeah, Henry's law. And that's actually just us noticing how the directional or the direct proportionality can be indicated through a gas law. Think about, V1 over T1 equals V2 over T2. So this is the same scenario. We don't use it like very often, but you will have one or two that you'll have to attempt on your own. So solubility over pressure, as long as they're in the same units from left to right, you're in a good place. So this could be in atmospheres. This should be in atmospheres maybe. This might be in grams per milliliter, or grams per milliliter, or grams per liter, grams per liter. As long as they're in the same units, it will work out for you. Okay? Thumbs up when I can move on. All right, and I'm videoing, so little bits and pieces that you might want to go back and watch me too. Okay, now we're getting to the concentration side. So I know you guys have dealt with concentrations your entire life. Who likes really sweet tea? Like, I know a lot of us are from the South, and we're like, I like it really sweet. Who likes unsweet tea? I mean, sometimes I like to, right? So who's ever had like too concentrated sweet tea, like too sweet? Okay. So eventually it would be. But yeah, so we know that we can always just reference, oh, this is too weak, this is too dilute, or this is too concentrated. Those are more qualitative terms that we'll use just to say, hey, I got too much or I got too little. It doesn't really put a number on it. So what we start to do is we say, well, can we describe that in a numerical form as well, which is our quantitative reasoning. So things like molarity. You remember molarity? It's the big capital M. What is molarity? Moles of solute stuff, okay, in liters of solution. So that essentially is a concentration, right? That is how much lemonade powder did I put in my liter, my pitcher of lemonade, or how much Kool-Aid powder did I put in my liter of Kool-Aid, or how much sugar did I put in my pitcher of sweet tea. So you can see that in many, many senses. Now we're going to describe molarity, which is what we're starting with because you're familiar with it, but then we're going to move on to molality, percent concentrations. Yes, that's it. So I want to make sure I'm doing enough examples with you before you go. And I know we'll see you later. All right, so we're looking at basically quantity of solute compared to quantity of solvent or solution, and that's going to give us some context to how concentrated something is. Who's ever seen, like at the grocery store or the drugstore, like 3% hydrogen peroxide, 97% isopropyl alcohol, 50% such and such? So those percentages are more the general population, where they wouldn't put molarity on there because that would scare the bejesus out of somebody if they're at the grocery store. What is this 2 mol for lemonade? What does that mean? Okay, so we're working with molarity first though. All right, so this is your definition. Number of moles of solute per liter of solution. So we kind of know that reference at this point. I'll go over this little blue section in just a second. So if you're not writing anything down but this, I understand. And then as you go, you should be able to speak that in the kind of more advanced manner. We don't say that's 2 molarity. We say that's 2 molar. So like a molar in your mouth, like a tooth molar, that's how you say it. So what does 2 molar concentrated sodium hydroxide really mean? Let's take that and put that in the reference up here. That means what? 2 moles of what? Sodium hydroxide, NaOH, in 1 liter of solution, right? SLON is solution for me. And that likely is an aqueous solution. We usually don't deal with anything but aqueous solutions because oil solutions and hexanes and pentanes and gasoline, those mixtures are not really friendly. Water is friendly, so we'll deal with mostly aqueous solutions. So basically you're interested in molar, and what does molar mean? Now, the intensive property up here says it doesn't depend on the amount of solution you have. So I can have 1 droplet of 2 molar sodium hydroxide. I can have a beaker full of 2 molar sodium hydroxide, or I can have an ocean full, okay, of, that's supposed to be Africa, some stuff, okay. I can have 2 molar sodium hydroxide, okay. Doesn't matter how much I have, it's a ratio. It's I have this much and this much, I have this much and this much, I have this much and this much. So I can give you a glass of lemonade from my pitcher. Does it taste different than what's in the pitcher? Unless I didn't mix it, it shouldn't, right? So that means that it does not depend on the amount I have. Okay, so as we solve types of problems, you know that this is the general way of life, right? You know you write down your givens. You know you look for your question. And then you know you have to evaluate and like, does this kind of make sense? Because if it doesn't make sense, you probably messed up someplace making sure your unit's canceled and so forth. So this one, I'm not sure. I copy this? I sure did. Okay, so these are, I'm going to do a couple up here, and then we'll go through some of the ones on your paper, okay? Write down these examples for yourself. Word problems can get fishy, so making sure you write down your givens is the main point here. All right, so what's the molar concentration of a 5.00 liter solution containing 4.3 moles of sodium chloride? That's the question. Let's back up. What are my givens? 5.00 liters of solution. Okay, what else? And you can put MOL for moles, right? Sodium chloride. And what's my question? That is a side question, rhetorical. What is the molar concentration? What does that mean? Say again? So molar concentration means solve for molarity. Yes, yes. Okay, so we're not going to read the question again. What's the definition of molarity? What are the units? So moles over liters. Do I have moles? Do I have liters of solution? Bada bing, bada boom. Done. Let's go. What do I have to do? 4.3 moles of NaCl in 5.00 liters of solution. Do a little double check, moles per liters. I'm in good shape. And calculate. I'm depending on your quick calculator fingers. 4.6 or 0.46. 0.86. You guys gotta enunciate. I'm getting old. Yeah. Okay, so how do I write molar? Big M. And if I want to get real fancy, but 0.86 molar sodium chloride. And that, my friends, is my final answer. Whew. Okay, that one was nice because it gave us the units that we wanted. We moved on. Assessing the situation, yeah, like that's not even 5. That answer makes sense because it's less than 1. Okie dokie, moving on. Now, this one is going to give us a little bit more of a challenge because we're going to start units that are not in molarity. All right, so if you've ever been to the doctor, they have to the nurses there and other medical officials have to make sure that your fluids stay in check, right? So they're checking for your saline levels. What's saline? It's actually where salt is in your body, right? You want to make sure that you don't have too little or too much because if not, your cells burst. What's that called? Hypotonic. What's it called when your cells shrivel? Hypertonic, and you want it to be, what's it called in the middle? Triangle, same sides? What? Isosceles? Isotonic. Isn't it called isosceles? Two the same sides? Okay, man. I just said triangles on the same side. My bad. Okay. Okay, so it's been like way too long since I had geometry. All right, so if nurses don't check the concentration solutions of saline, they could potentially cause you to die. Okay, uh-oh. That's not just an but saline solution contains 0.9 grams of sodium chloride per 100 milliliters of solution. What is the molarity? All right, so we have givens, right? What are our givens? 0.90 grams of sodium chloride, and what else? Okay, and I'm trying to give us our sig figs. Make sure we're cool with that. Okay, and it's looking for molarity, right? Again, John, what's molarity? Wonderful. So this is what we want at the end. This is what we want. Do we have either of those? No. All right, what do I have to do with this first? Take it to moles. Okay, Mikado, tell me what I'm writing. You guys calculate, please, so we're moving along.
So you're going to write 1 mole of NaCl.
Okay, so converting to moles of sodium chloride requires I cancel out what on the bottom.
And then you're going to write
0.55. Nice, thank you. So 58.55 grams of sodium chloride. Why am I putting grams on the bottom? You want grams to cancel out. Wonderful. And do I have a calculation? I'm trying to do this with you so I'm not going too fast, but not too slow because you're already checking out on me. 0.015, and I'm not stopping because is this my final answer? No, I'm just making sure I have all my cats in a row, all my ducks in a row. Okay, cats are crazy cat lady. All right, so I'll show you guys a funny video later. Remind me about cats. All right, so I have 100 milliliters of solution. I want to get that to what? Liters. Now, normally you would just do what? So you can move the decimal back 3 times because that means you know how many milliliters are in a liter. How many? 1,000. So if you move the decimal back 3 times, you can get that, or you can use dimensional analysis, which requires you to know that King Henry died how? And where's my milli? At the M, and then where's my liter? The base, and how many decimals away is that? 3, so that's 1, 2, 3, 1,000. Okay, so 1,000 milliliters is equal to 1 liter, and why am I putting milliliters in the bottom? To cancel, oops, that didn't mean cancel 1,000, meant cancel the milliliters there, but 1,000's still there, so that's 0.100 liters. What do I do with these values now? Say again? Divide them, yeah, put the moles in the top, divide by the liters in the bottom, and I arranged it like so. And Will, what's that? Guys, everybody calculate with me. I don't want to wait on the class for make sure that you're with me. And how many sig figs should that be? Will? How many sig figs are up here? And how many here? This one has 2 sig figs, and this one has 3 sig figs. So this one should be at what? 2 sig figs, so the answer should be 0.15 molar sodium chloride. And that is our saline solution. that they put it in IV bags and then you get to make sure you're healthy. Thumbs up if I can move on. That was just a grams to moles and milliliters to liters question there. And then at the end we have to divide to get moles per liter to get molarity. All right, let me pause on molarity for a bit, and then we'll practice more with that. I'll pick out a harder one to do, actually. Yeah, let's do this one. I love making solutions. I do. What solution am I making? Sodium sulfate. So what solution, though, because I can't just make sodium sulfate, right? 0.24 molar of what volume? 1.5. Okay, so I've got a lot of givens here to work with. This one's the one to write down if you're somehow not writing anything else down. 0.24 molar sodium sulfate, and I'm making this concentration at what volume? 1.5 liters. And what's the first question asking for? How many moles? Question moles, and that's assumed to be sodium sulfate, remember, because that's our solute there. Do I need to measure out to make the solution, and how many grams is that? So another question will be how many grams of sodium sulfate is that? Okay. Now, I haven't started with molarity and volume yet, but do you remember the golden rule when you have molarity and volume? You multiply them and you get what? Moles. And other than Meredith, does anybody else remember that? Okay, write this down for yourself then, and then I'll talk to you on the units perspective. Omar, are you with me? Okay, thank you. So M times V will give you moles. Every single time it will, and that's because of the cancellation of units. So if you have moles per liter, and that's our molarity, moles per liter, and we have volume, now volume does have to be in liters, which in this case it is. When you multiply by liters, what cancels? Say again? Liters, right? Liters cancel, so we get moles. So that's the logic behind it. It's not that we've memorized this creative, fancy formula. M times V gives us moles. It's we know how to cancel units. It's not a secret at all. All right, so let's just kind of plan ahead. If I take my molarity and my volume and I multiply them, I get moles, right? Check, first answer there. How do I get to grams? Use the molar mass. Next step, we're done. Okay, let's go. So molarity, 0.24 moles of sodium sulfate divided by this with respect to this volume or this molarity here, that is assumed to be in what? 0.24 molar means what? 0.24 moles in 1 liter. Remember, molarity has a standard comparison to 1 liter first. And then what we will do is when we multiply by 1.5, it should be more, right? So at the end, our moles will be more than what's in 1 liter. Calculation? And now let's just pause. I'll write it down, and then you guys will tell me does this make sense. So that's 0.36 moles of sodium sulfate. Does that make sense? I got 1 liter that has 0.24 moles, so I have a half more. Like I have a half a liter more. So I should have 1.5 times greater than that. Well, half of 0.24 is 0.12. We'll add 0.12 to that 0.36. Math. Does that make sense? Okay, so then 0.36. Does anybody have sodium sulfate's molar mass? One more time. And why am I putting it on top? To cancel moles on the bottom and get grams on top. And mass? And that should also make sense. What's about a third of 150? Like 50, and you said 50 what? And sig fig should be 2, so it'll be 1, or it should be 51 grams. Okay, let's talk about the logic behind this whole idea first, and that's going to get us into the next set of problems. So, I'm going to scroll up there a little bit for you guys. So I had to make 100 or 1.5 liters of this solution, right? Well, what kind of glassware do you think I would be using? Anybody? What kind of glassware does a great job at volume, at measuring volume? A graduated cylinder. A beaker is not, is literally the worst thing you could use because it is not correct, okay? A flask, you know those flasks like this, the early water flask, they're not really all that great either. They just kind of tell you a capacity. Like, this is approximately 250 milliliters. Take your pick, right? They just give you a capacity for reactions and that kind of standpoint. So what I would have to do is I would have to get a really, really, really precise form of measurement to make exactly that concentration with exactly that many grams in there. Now, do I have a mole balance back there? No, what kind of balances do we have? Grams. Okay, so you're going to write down how you would prep this. You guys are prepping solutions on Wednesday. So the idea is that I can do the math. I know the volume I should have at the end. I know the concentration I want, but I can't really measure out moles on my balances. I have to measure out grams, which is why I had us convert to grams. So then we would backtrack, and the process would be take 51, and I would actually ask to be more precise. I would go for this one. 51-ish grams of sodium sulfate, and put into this is the new one, it's called a volumetric flask. Volumetric means it's precise to the volume you're indicating, and the flask looks kind of like a flask. I'll show you a picture in a second. So take 51 grams of sodium sulfate, put into a 1.5 liter volumetric flask. And you are writing this down because when I go to the next page, if you want to write it down, I'm not going back for you guys. Sorry, darlings. And fill with water halfway, and I'll tell you more. So I'm walking through the process of, I've done my math, I've done my background. I'm going to take that 51 grams of the sodium sulfate. I'm going to put it in this fancy flask called a volumetric flask. Now, volumetric flasks come in literally every volume you could imagine. Here's my favorite one. Hold on. So these are my Barbie and Ken ones. These are 10 milliliter volumetric flasks. They make exactly 10 milliliters at the edge line right there. I'm not passing from the smaller ones are more expensive because they're very, very fancy. These are probably, I don't know, $30 to $50 each. So the volumetric flasks don't have any graduations except for one, and it's the one volume you want. What one volume do I want here? 1.5 liters. So I would grab the 1.5 volumetric flask and move on. I'm going to fill it with water halfway, and then just like you do with a normal solution, what do you do to make it mix? Stir it or swirl it, right? Whatever you need to swirl it, okay? And after that, we'll fill with water until the etched, bless you, mark. The etched mark is, I have a picture that I can show that to you better, but on the neck of this volumetric flask, there's like a little white line around it, and that's exactly the volume you're indicating. So after you swirl it, you fill it with water all the way to the etched line, you have made your solution. It has diluted itself from 51 grams of pure salt into a volume of water to make the concentrated we wanted, which was 0.24 molar. And then we'd label it, and we'd put it on the lab station. Okay? Can I move on? Yay, nay. Thumbs up, thumbs down, something. Let's just do green breather. Okay, let me show the picture of that first, and then we'll stop for a minute. So, that picture is right here. So this one on the bottom allows us to take this volumetric flask, we put our salt particles in there, we fill it up halfway, and then we do what? Swirl it, and you can see it's got a nice like bottom area to swirl in. And then we're going to fill with water until the etched mark, which is where your meniscus falls. Now that's assuming you're starting from a powder part, a powder solute. I could take a super duper concentrated solution, like the acids we have in the back, which are like 16 molar sulfuric acid. Okay, that'd burn your eyes out. Okay, so I'm not going to give you burn your eyes out acid. I will give you like 1.6 molar acid, and then we call it a day. So how do I take this guy and make it go to 1.6 molar? What do I need to do to my solution? add some water, right? Well, I have a stock solution like yay big of that. Do I just add water to that and say, okay, here we go? No, I'd be contaminating my entire sample, and then I have to buy more. It's like $100 a bottle probably. So what I would do instead is I would take some of the concentrated solution out, put it in a new flask, and then do it. And then do all the rest. Do the add water, which would dilute the 16 molar acid to a more friendly 1.6 molar, whatever I was adding. And I would then fill it up to the mark, and then that would be our diluted solution. So I can dilute from liquid or solid is what I'm trying to tell you. Like you can take really two concentrated coffee and you can add a little water, and it's more doable at that point. So similar issues, let's go ahead and solve a couple with the molarity formula. Here's your information, write that down first. How do you write the formula? So this is similar to the idea we were just working with. We have a really concentrated, probably expensive, probably hazardous stock solution, which behind that door I have a stock room, which is where I have all my stock solutions. They're very concentrated. And many times we don't work with that style of solution because it's just too dangerous, or it's too concentrated, or it's too expensive. So we dilute it to a more usable form. When we dilute it, we are diluting with water, and when we dilute it, we always have our diluted concentration in the volume we want to make, whereas many times I'll use M1 to represent my concentrated solution, and I'm going to use just a tiny bit of that to make the diluted solution, just like you would with concentrated Kool-Aid or other drink. So using this logic, this formula, let's solve for this problem. All right, so how many milliliters of the stock solution of 2 molar magnesium sulfate would you need to prepare 100 milliliters of 0.4 molar sodium sulfate? Let's label as we go. First thing you see is what? Question of milliliters. Okay, what else? Magnesium sulfate. And since it's the same thing, I'm not even going to write that because I'm not changing the identity. What else? So we're pulling out all of this information. Now, I'm going to label that so it looks kind of like the formula does. What would you label the first bit of givens up here? M1 and V1. So those were given as a scenario together, so I must utilize them together. The second scenario was if you were to prepare that volume with that molarity. So what would you label the bottom two? Yeah. This is V2 in this respect, and this is M2 here, and that's allowing you to see that the volumes are in what unit? Milliliters, and the molarity should be in molar, right? Capital M is molar. So I've got everything I need, right? I'm good, and I can plug into what formula? What's that one? I can't see it. The dilution equation, which is V1 equals M2 V2. M1 V1 is equal to M2 times V2. That looks really similar to our gas laws, right? Similar to algebra, similar to the givens, similar to let's go ahead and isolate thing we're looking for, which is what here? V1. So how do I, you're good. How do you get, it doesn't matter as long as you put the scenarios together that came together. So how do you solve for V1? Divide both sides by M1. So M1 cancels, V1 gets isolated. So V1 is equal to M2 times V2 over M1. What's M2? 0.400 molar. What's V2? 100.0 milliliters. And what's M1? 2.00 molar. Calculate first and then we'll make sense of it. And somebody have a calculation for me? V1 is equal to 20. Yes.
So for just with that, the dilution equations, it doesn't matter if the volumes and milliliters are different.
Right. So that was my other point here. Molarity is moles per liter. But as long as my units of volume are in the same volume, I can utilize milliliters or liters. Usually we don't do anything else other than that. Because really I'm looking for a specific volume, and as long as everything else cancels, which in this case it does, what cancels over here? Molar and molar, I can utilize that. Now, the purpose of doing this was to actually make a solution, right? So I've now said, I have a super concentrated solution, I want to dilute it, I need that much of my original solution. Have I diluted it yet? No, because it's still what? So what's still the concentration? 2.0 concentration, right? So it's still of the stock solution, which is 2 molar. So I can't just be like, yeah, I got 20 milliliters, I'm done, right? What do I have to do with this now? I have to take 20 milliliters of stock solution and add it to a same cadence, right? You just wrote this down. What size volumetric flask? How big? 100, because that's the diluted volume, right? I want a 100 milliliter diluted solution. So to a 100 milliliter B flask, you guys know what that means? Volumetric flask, okay? And what? Hold on, add half filled with water, and then what? Swirl, stir, whatever you want to say, and then, yes, fill up to etched line with water. That's the complete process. You do the calculations, you say, does this make sense? Yes. Pull out the information, or pull out the volume you need, which is 20 milliliters. Put it in a smaller container, that would be your diluted, smaller volume you're making for like a lab standpoint, and then fill it up. Alright, get up and take a stretch break. Go talk to me about life and chemistry. Make sure you all put your name on the list if you're going to be gone from my classes. And make sure you Alright, back to me. 10, 9, 8, 7,
6, 5, 4, 3, 2, 1.
6, 5, 4, Alright, cool. Thank you, Caleb. I'm 11. Alright, so we got two more types of calculations, and I got 15 minutes to get this wrong. Write down the next style, and then as you're writing, tell me what you notice is different from molarity. It has kilograms of what? Of what? Solvent, not What was molarity? Liters of solution, whereas this is kilograms of solvent. And what else is different? Well, I already got that one. It's what?
It's a lower
It does have a, thank you, I wanted the blatant one. The blatantly obvious one is what? It's a lowercase m. So when you write m, make it meaningful. Are you writing a capital M? Are you writing a lowercase m? Or are you just writing just some like little lines that I don't know what it says? So those of you who are struggling with your fine motor skills, I have given you lots of practice of capital M's and lowercase m's. So that's our given set of units for molality. And then I know this sounds like some sort of jungle cat, right? We say it as malal in the distance. Okay, so 2 malal solution. I think it sounds like a jungle cat or something. Like, look at the malal in the distance. It's green and purple. You can't see it in the plants. It's versus molar. Molar? Wow. All right, so we've got 2 totally different units here. Now, are they still representing something similar? Yes, they are still representing a concentration. We will still use it exactly the same way that we did molarity if we needed to. In this case, try to keep it interesting. Okay, so what's the molality of a solution that contains 55.4 grams of potassium nitrate in 300 grams of water? Whew, okay, what is this asking for? Moles of what? Who? Potassium nitrate in. Well, no, give me just the units and then we'll jump here. So molality is moles of potassium nitrate in kilograms of H2O, right? That's our solvent. So that's still keeping you in check. Like, do I know what solute and solvent is? Okay? So then our givens here, 55.4 grams of potassium nitrate and 300 grams of water. I know you guys can pull your givens out there. Okay? Caleb, what do you want to do first? Knowing that up there is what we want. Convert what to moles? Potassium nitrate. So we want to take this to moles because it's the solute, and we want to do what with this? Convert to kilograms. And then we're going to do what? So put in the equation and mathematically divide. Thank you. Okay. So 55.4 grams of potassium nitrate, and I do not know that molar mass. 101 point what? 11. I need secondary calculations. Frank, pick it up. I need to fix that. Okay. So 1 mole of potassium nitrate is 1. Did anybody else secondarily calculate? Thank you. 0.1. Making sure we're all checked in still. Okay, so I'm putting grams on the bottom because I wanted to cancel. And then approximately, don't even calculate yet. Approximately how many moles is that? About half. So about 0.4 something. What is it? Oh, no, sorry, 0.5. Beautiful. Okay, so there's our moles. Not my final answer yet, but close. All right, turn your phone down. Thank you very much. And then what's our conversion here between grams and kilograms? Move the decimal which way? 3 times to the left, right? And that's because kilograms are small, are big, grams are small, so there should be lesser kilograms than we have grams. But just in case you are not fond of decimal moving because you're not maybe successful in some way or form, then you should make sure that you do your 1,000 grams in 1 kilogram. I say this because we literally all of us have made that mistake. I grade your papers. I remember these things. I'm like, what did they do? Okay. So I have 0.3000. I think I didn't add a 0. Yeah, so there's 4 sig figs there. And with respect, 0.57 moles. 547 moles. Please, thank you. Someone. Oh, and when when you divided, Caleb, what'd you get? Guys, don't be slackers. You're going plus. I'm not saying Caleb is slacker. I did not say that. Kaylin. No, I talked to Caleb. Kaylin, what's the answer? Yeah, now I am. Now I am. I wasn't, but now I am. 1.823. Wow. Potassium nitrate. Can I get a second on that? Yes, thank you. And then how many sig figs? I need 3 because this one has 3. So that would be 1.82 milal. Okay. This is fine? Sure. Thumbs up when you're good there. Yes, ma'am. That's cool. I'll look back at your math. I'm running the flow with who gives me math. So, now there's, actually no, I'm not ready to do this yet. Okay. Oh, I have a joke for you. I will. I'll show you later. Good. Oh, that hurts. Oh, shucks. It's in the name of science. Take your $5 and clear out. 5 molar solution. It's kind of dark, but it's there. Okay. You get it? Yes, if you don't get it, we'll work on the molarity some more. Okay. And last but not least, percent solutions. I'll put these up for during intervention time for you, okay? Okay. Percent solutions are the easiest ones to do. Write down the expressed volume for volume. I'm watching the time here. I'll shake cat video during intervention if I have to. I have 5 minutes. These are examples of percents. Percents are always set up the exact same way. Thing over total. Part over whole. Whatever you're talking about with reference to solution, it's always going to be solute. So the smaller quantity over the entire solution. And I can ask for a variety of percents. I could ask for either volume by volume, which in this case I could give you volume as milliliters or liters, but as long as they're the same unit back and forth, they will cancel, they will give you a percent because you're representing them in a way that's comparable. I could give you, or ask of you, volume by volume, mass by mass, or mass by volume. Every single time, the numerator will always be referencing what? Excuse me? The numerator will always be referencing the what? The solute. The solute. The solute. And the denominator will always be referencing the total solution. Total solution. Total solution. And at the end, once you get your division done, what do you have to do to make it percent? Times by 100. That's why I said these are the easiest ones to down. Because these are ones that you've dealt with every probably math course ever. So let's go ahead and do this one, and then I'll pause and do the rest if we need to during intervention time. Take your question here. Tell me what's the solute. Ethanol. Okay, how many, and I'm doing a volume by volume one. How many milliliters of ethanol do I have? Okay, so milliliters of ethanol. And I'll divide that by what? Total solution milliliters. Okay, so this is where you got to read, not really about math, but read it. How many milliliters of ethanol is this? 85 milliliters of ethanol. Okay? Over what? No. No. What's the total solution? You just add the water and the ethanol. That's your solute. That's your solvent. How do you get solution? Okay, I said it was easy. You just tricked me. Oh, with water. I'm sorry. I'm making sure you're reading ahead. There's a question on the next slide that makes you think about water being a separate entity. My bad, guys. This is with water. No, dilution volume. Yeah. Let me read this. Let me actually read this out loud. Okay, so we have. I was trying to rush you. Shut down your computers, please. I'm sorry, we're gonna leave in a minute. So 85 milliliters. I'm sorry, I didn't mislead you. So diluted to a total volume of 250 with water times 100. And what is it? So 34%. 34%. Okay, we'll finish a couple more of these with practice that you require. During intervention, laptops up. Sorry about that. That's on the next slide. All right, bye guys. We'll talk during intervention.